So hello everyone, I'm Liliane-Joy, a master's student at EPFL in Switzerland, and I worked on this project during a master internship at Inria, which is the French National Institute of Computer Science, with Emmanuel Jeandel and Vladimir Zamdzhiev. So I will now present our work on Qimaera, which is a library in the Idris 2 language for type C variational quantum programming. So some quantum programming languages have already been developed by some companies like Google, IBM, or Microsoft, but also in academia. But the main problem with these languages is that they are not type safe, which means that some programs which may not be compliant with the laws of quantum mechanics are not detected at compile time and can raise errors at runtime. And this is exactly what we want to avoid. We want to be able to detect all the wrong programs at compile time. We mainly focused on variational quantum programs, which are hybrid classical quantum programs. And here, the main challenge is to be able to manipulate both quantum and classical data, even if they have very different behaviors. In our approach, we take the point of view of a classical computer that will, a programmer on a classical computer who will send instructions to a quantum computer. And then after all the quantum computation, will receive all the classical data through a communication protocol. For this project, we chose the Idris 2 language because it introduces two constructions, dependent types and linearity, that will allow us to write only programs that are compliant with the laws of physics. So let me first present these two features of the Idris 2 language. So the first one is dependent types. So basically in Idris, a type can depend on a value. Here I give a very simple example, the vector. So what is a vector? It's a list with a fixed length, and this length is part of its type because this type is parameterized here by a natural number, the length. So an empty vector is only a vector of length 0. And then to build a vector of size n+1, so here it's the successor of n, we need an element and a vector of size n. And using these dependent types, we can now create like a small function, the function append, that will take as input a vector of size n, a vector of size k, and output a vector of size n+k. And these dependent types will allow us to ensure some correctness or mathematical properties in our data structures and programs. The second feature of Idris 2 is linearity. So in each function, each parameter has a multiplicity that could be 0, 1, or omega. The parameter 0 means that the argument will be erased at runtime. 1 means that it's linear, so this parameter has to be used exactly once. And finally, the multiplicity omega means an unrestricted usage. So here we can give an example of linearity. What we are trying to do here is to take as a linear argument, but then in the function itself, we are trying to use it twice. So here we are copying it. And this will raise an error message saying that we are copying this argument, which is not allowed. And for us, this is very useful because we would like to enforce the non-cloning theorem for qubits and prevent the user from copying them. Well, now using these tools, we can start coding. So first, we made a clear distinction between two parts. In the first part, we are only interested in quantum circuits as mathematical objects. And then only in the second part, we will do all these effectful quantum computation where we apply these quantum circuits to some qubits. So first, for the unitary mathematical operators, which we can see as a set of gates and wires, we created a new data type, which is called unitary. And here we also use dependent types because we parameterize this type by a natural number, which is the number of wires in the circuits. So this type has 4 constructors. So the first one is the identity, which is just an empty circuits for with n wires and absolutely no gates. And then we can build circuits with the gates. So with the first constructor here, the Hadamard gate, we just have to specify the index of the wire on which we want to apply the gates. And then the compiler takes an implicit proof that this index of wire actually exists. So we cannot apply a gate on a wire that does not exist, which is materialized by the fact that this index j has to be smaller than the overall size of the circuits. We do exactly the same with the phase gates. And for the control not gates, we ask for 3 conditions: that the control and the target exist, and also that they are different. This can be used to create some very basic circuits. So here, for example, it's the circuit that is used for preparing the belt states. It's first a Hadamard gate on the first qubits, followed by a control not gates. So here we create a unitary operator with 2 wires. We apply the Hadamard on the first one, and then this control not on both of them. And here, all the proofs are automatically inferred by the compiler. We don't have to specify anything. Then we can use some basic function like the composition. So this is sequential composition, here parallel composition, where we use dependent types to ensure that the size of the circuit is correct. Here we can build the control version of a circuit, and here the adjoints. And we can use all of this with a small example, which is the quantum Fourier transform. It has a non-trivial recursive pattern, but actually the code is not very long, and it's like normal recursive function. So here we are using all the small functions defined before, like rewrite, compose, tensor, to build recursive the pattern and then build the whole circuits. And here, at some point, we need some very small lemmas to help the compiler infer the proofs. However, most of these lemmas are quite trivial, and we can hope that in the future, as the theorem prover of Idris 2 will be improved, we won't have to specify these very short lemmas. Now that we know how to build the circuits, we want to be able to do some effectful quantum computation. So how can we apply the circuits to qubits, or more generally manipulate qubits? So here we have to be able to manipulate quantum data, even if its behavior is very different from classical data. And by doing this, we don't want to affect all the classical computation. So in particular, we want to apply the non-cloning theorem, and for this, we will use linearity. So in particular, we created a new interface, which is called QuantumOp, that define all the basic operation that we will allow on qubits. So we want to be only able to create new qubits, apply a circuit to some of the qubits, and finally, we will be able to measure the qubits and nothing else. To implement correctly this interface, as I said before, we use linearity, and in particular, as we want to send and receive instructions from a quantum device, we will use a linear I/O monad that we called R in our implementation. And then as a quantum operation, well, quantum computation is basically a sequence of quantum operation, we chose to represent them as a quantum state transformer. So basically, it's just an operation between an initial quantum state to a final quantum state that will at some point return some data to the user. And for this, we use this linear IO monad that we defined previously. For more convenience, we also introduced some unique qubit identifiers with the data type qubits. So they're only pointers to qubits, but they do not represent the quantum state, as the quantum state cannot be represented by the qubits individually. And this is the implementation of the interface. So here we have the function to create p new qubits. So it's just a quantum operation between a quantum states with n qubits to a state with n plus p qubits. And the user will be returned a linear vector of p qubit identifiers for all these new qubits. The second possible operation is to apply a unitary circuit to these qubits. So here we just give the vector of qubits on which we want to apply the circuits. We provide the unitary circuits, and then it's just an operation from n qubits to n qubits, and that's it. And finally, we wish to be able to measure some qubits. So here, once again, we specify the name of the qubits we wish to measure with a linear vector. And we go from a state with I plus n qubits to n qubits, and we return a vector of classical information, Boolean, with the results of the measurements. And all of this is executed inside the run function. So let's give an example, because it will be more clear to understand. So we took the example of QAOA, which is a variational algorithm to approximate solutions for combinatorial optimization problems. And in particular, we focused on the max cut problem. So basically, this is a back and forth process between quantum computation and classical optimization. So first, we have to prepare a trial state. So this is obtained by a circuit, by applying a circuit of depth P, which is a composition of cost and mixing unitary operator that we apply on n qubits on the plus state. Here, what is interesting is that these circuits are parameterized by some classical parameters, beta and gamma. Then we measure these qubits, and we feed the results through a classical optimizer that will output the new parameters, betas and gammas, to repeat the process. So now let's have a look at the code. So first, to prepare the trial states, we need to get the unitary operators. So first, the mixing unitary operator takes this classical parameter beta, and is just a tensor product of n time the Rx gate parameterized by beta. And the second one is the cost unitary operator. This one depends on the graph, so we have to give the graph as an argument. And in Idris 2, a graph can be easily represented using dependent types here, because it's a graph of size n. And it also needs the classical parameter gamma. And then we can just compose all of this. So here we provide the whole vector of betas for all the whole circuit, same for the gammas, the graph. And then we compose all the mixing and cost unitaries to get the whole circuit. So here the dot is the composition operator. Then the other ingredient is the classical optimizer. So how does it work? We provide the graph and all the previous information that results from all the previous iterations of the optimization. And it returns the new vectors of betas and gammas. So for our implementation, we did not code a classical optimizer, because it was not the aim. We just wanted to show that quantum and classical operation could be mixed together, not to implement a classical optimizer, so it just returns random numbers. But then the most interesting part is this one where everything is done together. So we wish to repeat this algorithm for k iteration with circuits of depth p. We also need the graph, of course, and then we return all the results of the classical optimizer with the guts. So first, what we do is we get all the results from the previous iteration with the recursive call, and then we feed these results to the classical optimizer with the graph to get the new betas and gammas. And then we can build the circuits. So as you can see, this is still in the classical computation because building a circuit is just a classical optimization operation. It will be applying it to qubits that is performed on the quantum computer. And here, so these are all the quantum operations that are inside the run function. So first, we create n new qubits, and then we apply the circuit to these qubits, and finally we measure them all, and we get the classical results in this cut here. And finally, we return everything. So as you can see here, we mixed quantum and classical information in an intuitive way, everything in a quite small function. Well, so we presented this library, which has a support for both classical and quantum programming, and it allowed us to implement some variational algorithms that are a back and forth process between this classical and quantum operation in a type-safe framework that does not affect all the classical operations that we can do. As a future work, we will maybe implement some other variational algorithms. And also something that we would like to do is having another implementation of our QuantumOp interface, because for now we don't have a quantum computer. So the implementation is made using linear algebra and matrix products. But of course, it would be better if we could have a computer to implement it directly. Here I put the link for the open source code, and the results are described here on a full paper on the archive. So thank you for your attention, and goodbye.